All right, hello. Welcome everyone to Meme Lecture 3, Part 3 of Differential Equations Made Easy. Today we're going to talk about some differential equations and how one can perform dimensional analysis to reduce the complexity of the overall analysis of a differential equation. And also, we are going to talk about the Lagrangians and Hamiltonians. These are a very common way to formulate partial differential equations and how to come in and try to build a little bit of understanding of why these quantities are so important and so nice. So the first part of this is going to focus on dimensional analysis. Now, when I say dimensional analysis here, I'm not referring to 1, 2, 3, 4 dimensions like you might in a geometry setting. No, I'm talking about here I'm talking about units. What are the units of a thing? So, for example, the basic gist of it is you can't add apples and oranges together, right? If you have units of something, you have to make sure that the units that you're putting together are consistent, right? So that's one thing. You can't add apples and oranges. You can't add meters to seconds. You can't add kilograms to newtons, right? They have to be of the same thing if you're going to add them together. Another important fact about this is if you're going to use any sort of function, it is often best that you're dealing with dimensionless quantities. The classic example that I like to think of is if you want to take a logarithm of some velocity, right? Meters per second, right? You have units of meters and units of seconds. Does it make sense then to apply the logarithm rules of meters per second and split that up into a logarithm of a meter and subtract? That doesn't make sense to me. Hopefully that sounds absurd enough to you that it also makes sense why you wouldn't want to do that. And so when you're inserting a function into a... Hold on, okay. I'm just double checking. I'm getting some error messages, but sorry about that. Units also provide a way to connect a whole bunch of parameters into a problem and reduce them down to the essential ones. I'm going to go over how to do that via the Buckingham Pi Theorem. So if you have two-dimensional quantities, how can you work together with them? Let's just lay down some ground rules. So if you have two quantities, A and B, they're only valid if they are of equal dimension. And I have dimensions here denoted with the brackets. So if you see a bracket, that indicates, hey, we've got some dimensions here. If you have two quantities multiplied together, the units themselves will also be multiplied. So if you have meters and then inverse seconds, you put those together, you're going to get meters per second. If you have A divided by B, if you have alpha divided by beta, the units are going to be the units of alpha divided by the units of beta. A similar rule applies to differentiation. If you have, you're going to take the independent variables dimensions and divide it by you're going to take the independent variables dimensions and you're going to use that to divide the dimensions of the dependent variable. Likewise, if you're going to integrate across a dependent and independent variable, you'll take the dimensions of the two and you will multiply them together. Another important feature of any sort of function with a dimensional quantity, it's only going to be valid if the internal quantity is either dimensionless or f is linear. And when I say linear, I don't mean like ax plus b, I mean like ax. Right, now ax could be a matrix and you're dealing with a vector, but it has to basically be multiplicative. You can't... Oh, did I drop? Yeah. Hopefully I'm not dropping. 1 second. Sorry about that. I'm just having some latency issues right now, so hopefully those will be fixed. As I was saying, if you have a function where you intake a dimensional quantity, it only makes sense if it either is dimensionless or it is some sort of multiplicative function, right? So if f of x is equal to kx, for example, where k is some other dimensional quantity, that's totally fine. But anything else, you want dimensionless quantities. So let's consider the oscillator. So the oscillator will have different units. So you'll have a mass unit, which will denote m. We'll have a length unit denoted by L and a time unit denoted by T. In order for this to make sense, if you specify that m has a mass unit and x and t have those length and time units, what are the dimensions of gamma and k going to be? Well, using a little bit of algebra, we will find that all of these terms must have the same dimensions, so they must have the same dimensions as that first term, and that first term has dimensions of mass times length divided by time squared. Therefore, using this dimensional analysis, we find that gamma has to have dimensions of mass over time, and that k has to have dimensions of mass over time squared. As an aside, using Leibniz notation, this dx dt notation for derivatives, is very useful in clarifying which units you can use by just simply dropping the d's, right? So you drop d's, and you'll see the units sort of spill out from that, right? So we have an x over t squared in that first term, and then we have an x over t in that second term, and then we just have x in that third term. So another thing we can do is we can try to extract or remove by non-dimensionalizing. And non-dimensionalizing means to basically take the dimensional variables, the dependent and independent variables, and making them dimensionless by basically introducing a dimensional term, in this case L or T, and then a non-dimensional term, which is the same but with the hats on top. And if we do that to this equation, we extract several L's and T's, and then we also pick up the X hats and the T hats. I do not know why I'm getting so many phone calls today. Anywho, in this case, sometimes variables like L will drop out entirely. Each term has a single L, and we can factor that out, which is good to know. We don't have to worry about the length scale at any particular moment. And then we can use the Buckingham Pi Theorem to take these different physical variables or dimensions and the parameters. And what it says basically is if you have n of these dimensions and p parameters, you can use that to extract p minus n dimensionless parameters, which are called pi's. So it'll be pi I. And essentially what this is it's a measure of nullity on the dimensional matrix. So if you look at this matrix below, we have the different colored terms for the different variables. They depend on mass and they depend on time. They don't depend on length because we saw that length sort of cancels out throughout. So the length scale does not matter in this problem. But we have these masses and these times, and we have 3 parameters, but we only have 2 dimensions. So we know that the nullity of this is going to be at least 1. Now, if for example, if you had a different if you had a different dimensional matrix, you could even have a nullity of 2, in which case you would have two dimensionless parameters, but more often than not, the nullity is going to be that p minus n. And that's at least guaranteed. You're guaranteed to have at least p minus n. You could have more if the nullity goes up. So in this case, if we look at these different parameters, we can shift things around. We can move the time variables around. And as it turns out, we can find a dimensionless parameter by specifying basically what the time scale is going to be. And if we specify a time scale, we have 3 possible choices, Tn, Td, and Ts. that basically corresponds to saying, hey, either the mass term is going to have this dimensionless parameter, or the damping term is going to have this dimensionless parameter, or the spring term is going to have this dimensionless parameter. But no matter what we pick, what we'll see is that all three of these, all three pi's that we can get out of it, they're all distinct from each other. So even though we have three options, there's really only one version of the same quantity, right? They're all powered versions of each other, right? So the pi for the mass option and the pi for the spring option are exactly the same. The pi for the damping option is basically the same up to a square root. So, or if you square the damping one and you invert it, so it's like to the power negative 2, you're going to get the same overall term. So it's really the same. It is, all three of them talk about the same dimensionless parameter, just in slightly different contexts. And so it's really one dimensionless parameter. It's just flavored a couple of different ways, depending on how you want to specify the time scale of the problem. Oftentimes, one will make more sense than another. And then the question rises is, what happens to the system as pi goes to 0 in each case? And that asks the question of like, okay, what happens as, what does it mean basically for these different variables? So if we look at the first and the third one, we see that as pi goes to 0, that's going to suggest something like either the mass is going to 0 or the spring constant is going to 0. And therefore we're going to expect some sort of damped behavior. Whereas for the damping term, or on the damping term, if we use that time scale, in that case, if pi is going to 0, gamma is going to 0. And if gamma is going to 0, that means we're going to a no damping case. And if we have a no damping case, we're going to get perfect oscillation. Hello, Trippy. Happy to see you here. Anyway, moving on. Nondimensionalization and the Buckingham Pi Theorem are useful for most differential equations. They can connect multiple models together if they share common dimensionless parameters. So in fluid dynamics, there is what is called the Reynolds number, and the Reynolds number represents basically a relationship between an inertial speed and a viscosity timescale. And so if you wanted to compare two different experiments in fluid dynamics, a common question you'll hear is, what is the Reynolds number? And if you have a low Reynolds number, you're often dealing with a highly viscous situation. If you're dealing with a very high Reynolds number, you're often dealing with a very turbulent situation. And then that will very strongly affect the dynamics of the equations. Often that is what dictates which terms are going to get dropped out. So if we go back to our previous example, right? Sad to see no one is here for lecture. Well, you're here, Drippy, and that makes me happy. And I'm sure others will watch it later. So the first two options for a dimensionless parameter, basically, if those are very small, you're going to be dealing with a more damped regime. But if the damping pi is small, that means you're dealing with a highly oscillatory regime. And that's a classic example. It basically allows you to say, oh, we're going to neglect damping. What does that mean? It means it means that we're dealing in a regime where that parameter is going to be small. Oh, we're dealing in a non-oscillatory regime. Well, what does that mean? It means that we're dealing in a regime where either the mass term, or the mass pi, or the spring pi are going to be very small. And there's a bunch of these things out there. You can actually look up on Wikipedia. Actually, let me pull that up. Hold on. Let me find. Hold on a second, let me show Wikipedia, right? There's a whole page of different common dimensionless quantities that come up. Here are some from biology and medicine. I couldn't tell you anything about these. You have a bunch of chemistry ones. Have I heard of any of these? Nope, but these, yeah, okay. These deal with like how chemical rates go. Oh, there's a whole page dedicated to just the fluid dimensions, numbers, and fluid mechanics. That's cool. Let me see. Kinetic of friction. That's a dimensionless number. That's a fairly popular one. The Fresnel number. That's used in optics, I know. Refractive index. That's another common one. If you have a different materials, will have different refractive indexes, and so if you have a very high refractive index, you're going to have light behaving one way, and if you have a very low refractive index, you'll have light behaving another way. Though often in that case, you have multiple refractive indices, and the behavior of the light beam is going to depend not even on this individual dimensionless quantities, but on the relation of multiple dimensionless quantities. Oh, fine structure constant. That's a popular one in physics in dealing with electromagnetism and levels of energy in an atom. What else is there? Any others that I recognize? Albedo. That's a common one in geophysics. That's basically how reflective is the snow or the cloud or the ocean or something like that. High albedo is an important cooling mechanism in that it reflects a lot of the sunlight, or it keeps things cool. Let's look at some of those ones in fluid mechanics, though. There's a whole bunch. So, here's a fun relation. It relates different. This table here is actually pretty cool. I've never seen this table before. It relates basically different regimes or different numbers together. So you have the Reynolds number, relates viscous forces to inertial forces. You have the Peckley number. Yes, Peckley number relates thermal stuff to inertial stuff. You have the Prandtl number, relates thermal to viscosity. Let's see. Here we go. A whole bunch of fun numbers. Let's see. Which ones have I worked with? Drag coefficient. That's a very popular one you learn about in physics. The Deborah number. That's pretty cool. It relates basically the an elastic time versus a. Oh goodness, that's a. Is there help? No. Yeah, it basically talks about for viscoelastic fluids. It basically says what's the time of relaxation versus some other common time scale. I'm blanking on what that time scale is supposed to be. The Ekman number, it basically says viscosity to how fast the Earth is rotating. So, these explanations make me sound so stupid. It sounds like I'm reading it off, and I'm not. Let's see. Froude number basically takes the sort of baseline speed versus the speed of gravity waves. A whole bunch of these numbers. Where are some of the other? The Mach number, relation of the speed to the speed of sound. That's a very popular one. Peckley number we talked about before. Reynolds number we talked about before. Rossby number relates the rotation of the Earth to a sort of standard inertial velocity. Bunch of fun numbers. Anyway, distraction over. Let's resume. Yeah, so there's a whole bunch of common ones out there that people can use to talk about the different cases of fluids that they're investigating, or other physical phenomena, though my background is more in fluids, so I'm very familiar with the fluid numbers. So that concludes the talk about dimensional analysis. The next part is another common trope out of physics. The physicists love these numbers as well. It basically allows them to generate things like the fine structure constants, like, oh, it's this dimensionless number, and if we tweak it a little bit, we'll get slightly different dynamics. Though, I don't know how much investigation actually goes into what happens when the fine structure constant is 0. I don't know that. I just know that it exists. But from another thing from the physicists that is often stolen in mathematical modeling is the idea behind Lagrangians and Hamiltonians. Now, the physicists aren't going to like this, but they are two similar sides. They're not quite two sides of the same coin, but they're like two sides of different coins for an equivalent coin. So if you're an American, you have the quarter and you have the nickel, for example. Sort of like that, You can convert between them very easily without much complication. They basically come out of physics. They describe energy or the action of the system, and from that description of energy or action, you can get all the dynamical equations that you would want. You'll see them show up in control theory. That's a very common way where you'll see them. You'll see them to generate all sorts of dynamical equations in astrodynamics. But you also see them in machine learning and economics. Oftentimes there's some function that needs to be optimized, like some strategy or some portfolio that you need to that needs to be optimized. And this is a way to do it. It allows you to basically say, okay, we have a wide range of inputs and we want to generate a wide range of outputs. What a Lagrangian or Hamiltonian will do is it will take all the different functional data. It basically takes these Lagrangians and Hamiltonians. It basically gives, if you can find a minimum or an optimal point within it, it basically gives you an optimal profile to solve some problem. So to compare the two, though, sort of highlight their similarities, is that both of them operate on bundles within a state space. So the difference is the Lagrangian operates on a tangent bundle, the Hamiltonian operates on a cotangent bundle. What that basically means is that the Lagrangian sort of points, if you think about it in terms of a vector field, the Lagrangian is sort of pointing you along. You have some sort of manifold with a vector field on it. The Lagrangian basically flows you along that vector field, whereas the Hamiltonian tends to find some sort of isosurface which you ride along. That's sort of, that's not a full explanation, but it's a spiritually coherent explanation of what sort of happens, sort of what differentiates the two in a very high mathematical sense. You also have different variables, so you're also tracking different variables. So for the Lagrangian, you're tracking q and q dot. Q dot is the time derivative of q, whereas in the Hamiltonian space, you're dealing with q and p, which is a momentum. The equations of motion are a little bit different. The Euler-Lagrange equation in orange is a second order partial differential equation that basically says that the change in the momentum is going to depend on the change in the state variables. Hamiltonian says a similar thing. However, it is phrased a bit differently. Now instead of the momentum, instead of the time derivative, it is now defined explicitly in terms of the momentum. The momentum p is equal to the partial of the Lagrangian with respect to that q dot variable. They also work over different quantities. The Lagrangian works over the action, which has similar units to energy, but instead of a total energy, it's a sort of difference in energy. There's an action. There are some good videos that explain sort of what action is at an intuitive level out there by like Veritasium or something like that, if you wanted to know a lot more about what action is. Whereas the Hamiltonian just deals with strict energy. So it's your kinetic energy plus your potential energy. The underlying math between the two is also a bit different. A Lagrangian depends more on a variational principle. You're basically trying to optimize for the Lagrangian, you basically optimize for Q and Q dot, whereas the Hamiltonian has a more symplectic geometric feel to it, so P and Q are sort of coordinates on this manifold that tell you how you're going to travel about. And that connection comes through the Legendre transform. It's written a couple of ways. I like this way of it being written, where it's the Hamiltonian plus the Lagrangian is equal to PQ dot. What that basically says is that what it's saying is that if you add the two together, you're going to get out the kinetic energy. So you have a momentum term P and then a velocity term Q dot. And you have momentum times if you have a momentum times a velocity, you're going to get some equation in terms of energy. Now there's a factor of 1/2 that's missing there from the classical kinetic energy, but that too is sort of moved over to the other side. So if you want to derive the Euler-Lagrange equation, you start with the Lagrangian. Now, how to find the Lagrangian is a whole course in itself. It often requires a fair bit of knowledge of the system and how the kinetic energy and the potential energy are stored within a system. And with that, though, you can define the Lagrangian, and hopefully you can define the Lagrangian in terms of your state variables Q and Q dot, and also time. And what you're doing basically is you're trying to find that perfect Q, right? That sort of minimized Q. And that happens by taking a variation of it, which is often called delta Q. And that delta Q, scaled by epsilon, is added to this equation, or is added to Q and to Q dot. And what comes out is basically a Taylor expansion on L. And if you if you take that variation, you subtract off the original, you're going to end up with this delta S term, and this delta S term is going to have two terms, a dLdQ term and a dLdQ dot term. Now, that dLdQ dot term varies by delta Q dot, and that delta Q dot term we can integrate by parts, as we see in the green, into a delta Q term, and that delta Q term, and in doing so, the other term, the dLdQ dot term, picks up an extra time derivative. And if we plug that back into the original, we have a dLdQ minus ddt dLdQ dot term, all within a parentheses multiplied by a delta Q and a dt. Now what's clever about this is that delta Q is never specified, right? And since delta Q is never specified, if this is going to vanish, if delta S is going to be equal to 0, if we are going to reach some sort of stationary point or some minimum, it has to hold for arbitrary delta Q. Therefore, it's not the delta Q term that can vanish, it has to be the term in the parenthesis. Therefore, we can assert that the term in the orange has to vanish. Therefore, that term in the orange has to be 0. And that's pretty cool. And then to go from there to a Legendre transform, or to the Hamiltonian, you have to perform what is called a Legendre transform. And it's used to switch between a function of a variable and its conjugate. Now, a conjugate variable is defined often in terms of a derivative with respect to some function f, as we see. And what happens is basically, if you apply this Legendre transform, you take some function f of x, you can spit out the Legendre transform using this supremum expression here. And the supremum, if you don't know, is basically a maximum for real numbers. It is the least upper bound for the thing. So you find some least upper bound of p that satisfy overall x. And p is defined to be the derivative of f of x with respect to x, and if you can compute this, you find its Legendre transform. Now, in the case where now a fact about the Legendre transform is that it is in involution. So if you apply it once and then you apply it again, you're going to get back the same thing. A simple example that I'm not going to calculate it by hand right now, but you can do this basically at home, is if you take f of x as 1/2 mx squared, which is the kinetic energy, if you compute the Legendre transform for this, you're going to find that g of p is going to be 1/2 mp squared, and p, as we recall, is the momentum, and that momentum term, and this is a common expression for the kinetic energy when expressed as momentum. And in the case of a Lagrangian and a Hamiltonian, we'll find that the conjugate variables q dot and p are the conjugates to each other. Or that's what we find. We find that q dot and p are conjugates to one another. And what Hamilton's equations basically does is it takes that Lagrangian, or the Legendre, it takes that takes the Lagrangian and it takes the proposed Hamiltonian, and it sets it equal to pq dot. And if you take the derivative with respect to p and q, you're going to get the following expression. You're going to get dh dp is equal to q dot, and dl dq is equal to minus dh dq. And it's this second equation, and the second equation can be substituted in. You can replace one side of the the Euler-Lagrange orange equation for the other side, so you get d dt dl dq dot. Right, that's that you get that through Euler-Lagrange, and then you can use that definition of momentum from before, where p is dl dq dot, to get that dt dp is equal to negative dh dq. And using that first equation from before, we get that q dot equals dh dp and p dot equals minus dh dq. There's a nice symmetry that pops out in the Hamilton's equations, and that's the symplectic geometry part that I was referring to earlier. That nice anti-symmetric yet symmetric form popping out. A classic example of this is going to be the harmonic oscillator. So the action for a harmonic oscillator is going to be the kinetic energy minus the potential energy, 1/2 mq dot squared minus 1/2 kq squared. And applying the Euler-Lagrange equation, we get that mq double dot plus k dot q is equal to 0. Right? That's the spring equation we all know and love from that we were talking about earlier. Now, there's no energy loss here, no damping term, but that's fine. We don't need damping. We can compute the momentum of the system is mq dot by just taking the derivative of L with respect to q dot, and we see that doing that gets you mq. And with that in mind, we can then find the energy of the system is, we can find the Hamiltonian is equal to pq dot minus Lagrangian, and doing a little bit of algebra, we get that it is 1/2 or 1/2 mp squared plus 1/2 kq squared. And then applying Hamilton's equations, we find these two equations, p dot equals minus kq and q equals 1/mp. Now this is not quite as recognizable necessarily as the earlier harmonic oscillator equation in the orange. However, it is still the same thing. It's just it is written in a different way. So that happens. And you can show it if you just do q double dot. If you dot both sides of the q equation, you'll get like q double dot is equal to minus k over mq dot, and a little bit of additional arithmetic will get you back to that Lagrange harmonic oscillator equation. Now, another thing that can be done with a Lagrangian is it can be used to build up a PDE. Now, it works in a similar fashion as before, but instead of having one dependent variable, you have two dependent variables, in this case t and x. And in that situation, you're going to start with the same dl dq term, but then instead of just a dt dl dq dot term, you have a dt dl with respect to the partial derivative of q with respect to t, and then you'll have another term for the partial derivative with respect to x. And then you take the derivative with respect to x. And applying it to this Lagrangian here, you're going to get a wave equation. And what does this expression up here mean? Well, the first term is 1/2 du dt squared, right? It's 1/2 v squared. There's a missing mass, but we can recognize this as some sort of kinetic energy. In a similar fashion, we have a c squared, a speed squared, so a length over time squared, multiplied by du dx squared. So it'll have the same units as before, which is always important to check. But what does du dx squared means? It means basically that a gradient in this function u, a physical gradient, a spatial gradient in u, represents basically a stretching, right? Basically the potential energy, as you increase the derivative of something, you're basically stretching out a membrane, right? If something is nice and flat, it likes to stay nice and flat, but if you have something stretched out with a big derivative, that is a store of potential energy. And physical systems like to release that potential energy into some sort of kinetic energy, and that's what happens here in the wave equation. It's basically an acceleration. You have an acceleration term first minus a potential energy term being released. Another great example of a Lagrangian that appears is Maxwell's equations. If you've watched this enough, you know that I'm a huge sucker for Maxwell's equations, so I will always enjoy an opportunity to talk about it. And in this case, since we're working with the 3D Maxwell equations, which are the standard ones, since the magnetic field is divergence free, we can deduce that the magnetic field is going to be the curl of some vector potential A. And in a vacuum, we'll find that the electric field is going to be the gradient of some function minus the derivative of this vector potential with some scalar potential V. And that V is very important. That V stands for voltage, right? So if you've ever wondered what the heck voltage is, it's basically a gradient of voltage gives you some sort of electric field. If you're an electrical engineer, you probably know that you can get a little bit loosey-goosey of where you call 0 voltage and where you call positive 12 voltage. And that's why. Voltage is always going to be some sort of relative difference. If you're in a high school physics class, that's important to know. Voltage is always about relative difference. And this is why. The electric field is a gradient of voltage. And using these definitions, you can find that the Lagrangian used to derive Maxwell's equations are going to be the 1/2 of the dot product of the electric field minus 1/2 the dot product of the magnetic field. You can think of the electric field as some sort of kinetic energy within the system, and that the magnetic field is basically a potential, like a store of potential energy for the electric field. I'm sure the physicists will dispute the exact verbiage of that, but that's in short the idea of it. And if you expand it out in terms of V and A and apply the Euler-Lagrange equations, you're going to get back Maxwell's equations. Now, I'm not going to show that here, but that's one thing you can do with it. That would take a fair amount of time. Outside of physics, you can use Lagrangians to model the cost of some system based on a output X and some input U. You have some integrals, you have some Lagrangian input and output U and X, and you can relate X in terms of U via some function F. And if you use what's called a Lagrange multiplier, which if you've taken multivariable calculus you would recognize, you can find some U of t that will satisfy the following equations. And these equations down here are basically the Euler-Lagrange equations, but computed for an extended Lagrange multiplier term. Right, there's a relationship between this Lagrange multiplier lambda dot t, and the derivative of Lagrangian with respect to the output, and the Lagrangian with respect to the input, and the dynamics equations, lambda t times fu, or times f over u. these sort of equations are often used in control theory to say, let's say you have some sort of robot and you want to get it from state A to state B, and you need to know what inputs to give it. And this is the way to do it. You can compute these equations and solve for U, basically. And once you have solved for U, you can plug that into your robot, and the robot will just do the thing, ideally correctly. Yeah, everyone knows robots don't work the first time. Similar ideas also happen in economics, where you'll have economic factors X that you want to control for, like you want some stock price to go up or some profit generated by some strategy, and that's going to depend on the inputs U. If you want this sort of a profit, you're going to need to buy more stock, or you're going to need to sell more stock, or you want this option or that option, or some future or some forward or some other crazy trick, basically. The state space of purchasing economic stuff is a bit out of my wheelhouse, but a lot of the same ideas still do apply. And a final point that I want to make about all this Lagrangian Hamiltonian stuff is called the Ostrogradsky Instability. And this raises a fundamental question that I've seen a lot on Twitter. It's like, why do differential equations only cap out at second order? Right? If we go back to all these equations that we were looking at today, like the harmonic oscillator, the wave equation, even Maxwell's equations are a bunch of first order equations, right? What's the deal with that? Like even if you manipulate the Maxwell's equations, at most you're going to get some sort of wave equation, which I just said is second order. And why is that? And basically, what Ostrogradsky's theorem is that if you include higher and higher derivatives, you're going to lead to Hamiltonians and Lagrangians that are unbounded from below. And what that means, basically, in terms of a Hamiltonian, Hamiltonians are, if you think about energy, Hamiltonians are systems that like to track the energy. And if you have an unbounded state, you can have runaway solutions, right? You have very unstable runaway solutions. You have all this potential energy getting released. You can have just unbounded energy release, and that's not good, right? That sort of system is not physical. And therefore, in order for a physical system to be realistic, you can't have arbitrary energy release. This is a very common theorem you'll see in different, in a lot of like fluids and physics papers, is that they'll find that, in this sort of a setup here, we find that we can construct solutions to these PDEs that release arbitrary amounts of energy, but that's not physical. Therefore, we know that a system can never satisfy that. There's something wrong with that system. It gives us some conditions to understand the world just a little bit better. And so what happens, though, is that because these higher order systems are more likely to include these unbounded solutions, most systems are going to be second order. Exceptions obviously can be constructed to avoid this, but you have to include some sort of guardrail to prevent this thing from happening. You don't want your system to have runaway growth like that. That's just not physically possible. Is there any other thoughts on this? No. And with that concludes this talk about dimensional analysis, Lagrangians and Hamiltonians. I hope you enjoyed watching. If you like this content, you can like this video. You can subscribe to the channel. I've recently gained the ability to receive super chats, so if you wanted to give a super chat, that'd be pretty cool too. I think it'd be a real feather in my cap to say I actually made, even if it's like 5 cents, I made money on YouTube. That'd be kind of fun. Anyway, with all that, thank you for watching and have a good day.